Right. So welcome to the last day of lectures. We'll see less of Diane and Diana. They'll still be there at the conference, but again, if you get a chance to, we'll try to thank them together, all together later with a round of applause. But if you get to thank them personally, I think they would be very appreciated. Okay, so I want to keep on going on yesterday. I want to keep pushing. I want to do two things. So first, I want to go a little bit into the technical details. Right? We built this whole notion of robustness on the idea that a test statistic, in the most standard natural sense, has a limit distribution, and that's going to be some value. And the question is, if I have a histogram, I fix the x, and we've kept talking about fixed x yesterday, and so we'll be a little bit clear about how we can relax that. And I have a fixed x. I look at all possible permutations. I look at the histogram of those, and I ask the histogram as n gets bigger and bigger, what does it stabilize to? And it tends to stabilize to a normal, and we want to ask what are conditions under which both of these normals match, because since this is going to give a valid test in the sense that this is by definition, the true resampling distribution of Tx in the limit, p-values, for instance, are valid. And so if we pick up quantiles from the randomization distribution, and the randomization distribution matches the true resampling distributions, then we're getting bona fide p-value, correct testing apparatus, etc. And so we wanted conditions for that. And there are two things we kind of left a little bit aside. First of all, the technical details of how do we get PCLTs, or some sort of CLT that accounts for permutation of the data. I want to give some more details about what it looks like when we work those out. And the main idea is that there are two different angles of attack, and I just want to look at those in simple examples so that you can kind of have the conceptual difference, and then when you go on your own, you know how to do those. I want to talk a little bit about how to make it more likely that these things match, and we kind of gave away the punchline for that yesterday. It's generalization. If you can normalize the variances are going to match the variance of these two normals, and so the whole distributions match. So I want to do that for half of the lecture, and then in the other half of the lecture, I want to go back to the distinction between Fisher inference and randomization inference. So here, all we did was with observational data, and we had this two-sample test, or we have group 1, group 2. We wanted to ask if the mean was the same in both groups. This is very reminiscent of what people procedurally are doing when they do A/B testing, Fisher test, where the difference between who's in group 1 and who's in group 2 is that there was a random treatment assignment. And then we proceed to build a null hypothesis by saying, well, if there's no effect of the drug, of the treatment, then these treatment assignments are just labels. So I can build a placebo distribution by just reassigning labels at random. If that's indeed the treatment assignment mechanism that I'm using to reassign labels, I'm recreating the null distribution, and then I get validity. But I get validity that's not, I'm going to get validity that's not unconditional in the sense of drawing the distribution of X. I'm going to get validity that's conditional on X in the Fisher test, where the only randomness comes from, let's call it Z, who was assigned treatment or not. So these are two very different paradigms. I think it was a source of confusion to some extent when teaching this material, and so looking at for having taught this class for a while, and so putting them in the same notation, same framework, and asking what are the connections can be very interesting, and as we'll see, it even suggests the need for new methodology, and that actually will set us up for my talk at the conference. So everything is in everything. Okay, so let's do this technical part so that it's clear where these central limit theorems for histograms come from. So I'm just recapitulating on the notation from yesterday. So we have our data, which we collect in a vector X, so typically n-long vector, distributed according to some distribution, and then all we want to test is that distribution lives in some subset of all the possible distributions, so some subset omega naught of calligraphic P. And as we pushed yesterday, the key is that you want a null hypothesis, a strong null that's going to give, that's going to be sufficient for the randomization hypothesis, which is that for some group of linear transformation, we artificially restrict ourselves to linear transformation, but the group structure is key, as we saw. Whether I look at the distribution of X or the distribution of X after a fixed, let's say, permutation, the distribution of those is the same. And when we have that, we can build the test, because certainly we get something stronger, but certainly we get and need something stronger, but certainly we have that the evaluated test statistics are distributed the same. In fact, the full vector of the statistic evaluated at the G's has the same distribution regardless of which test statistic gets which permutation. And that's enough for the kind of natural construction of a test, which is look at this set of identically distributed test statistic evaluated at all permutations, pick up the 1 minus alpha quantile, and accept or reject depending on whether you're above or below the 1 minus alpha quantile. And so what we saw is that the group structure plus this invariance hypothesis is enough to tell you that the test is unconditionally valid. So an expectation over draws of your sample, you will reject under the null the prescribed fraction of the time, so alpha of the time. That was the construction for yesterday, and we dug deep into that via two examples. So I'm just reiterating the notation. We had one example where we had n observations without less than, we want to test the value for the null. Without loss of generality, we test that the value is 0. And one way of doing that is, well, if the mean is really 0, as long, kind of intuitively from an engineering perspective, a good way of getting power if the null is not true is just using the sample average as a test statistic. A good null distribution would enforce this null, so flipping the signs at random seems like it's going to build a good null. And if I want validity, I want the group acting on, I want the linear actions acting on this to be a group, and the signs flip form a group. So that was fine. And then we had the two sample tests for the mean. A good test statistic is just going to compare the sample average in one group to the sample average in the other group. And then when I use a group of permutations and apply them to my vector of data, I'm effectively reshuffling who's in the first group and who's in the second group, as if as if group labels didn't matter, and I build my randomization hypothesis this way. So very intuitive, but we also got, because of this group structure and this randomization hypothesis, that the test was exactly valid. And that's really the big, that's really the big payoff, right? We get validity of the test without neither relying on asymptotics nor on specific distributional form assumptions. And that's kind of what we're excited to deliver. Okay, and so we distinguish between the strong null that's sufficient for exact validity and the weak null that's sufficient for asymptotic validity. And then we had this kind of discussion about what's the right marketing for this method. Do you want to say, this is what's important, but if this fails, I have the weak null as a robust backup telling me at least I'm going to be asymptotically valid if I have enough data? Or do I want to go the other way and say, the standard reason people use tests is that under weak condition you have asymptotic validity, and then as a sort of additional special perk, you get exact validity under conditions that you don't think you'd ever satisfy, but that make you hopeful that small sample behavior is going to be better. So this has nothing to do with any of the technicalities. It's just how do you want to kind of write the introduction of the paper. Okay. And this is a little bit the discussion we just had. So you can interpret this weak and strong null distinction with two different mindsets. As we said, either asymptotic robustness, where you want the exact test and you want the weak null as a safeguard, telling you you still get asymptotic validity if the strong null fails, but n is large. Or you could think of exact validity as a special property, a procedure that has asymptotic registering property alpha quite generally, so you think the weak null is satisfied typically in practice, but retains exactness properties in an infinite sample. So that would be sort of going the other way. And maybe this is how we think about the usual t-test. We don't like the usual t-test because it's exact when data is Gaussian. We don't think that the data is Gaussian. We like the usual t-test more for its guarantees in the asymptotic regime. So in terms of developing new methodology, I'm sort of sympathetic to the latter. The condition that for your procedure to be competitive in practice, the sine qua non condition is really that in the practical case, so large N but really weak assumptions on the DGP, you're getting the same validity as your competing procedures. And so as we're going to move towards regression, that's going to be the t-test. Okay. So this weak null, strong null, the weak null is very clear. It's whatever in your application is sufficient or even better equivalent to the randomization hypothesis. For the strong null, we had a recipe to find it. You find the standard limiting distribution of your test statistic with no permutations whatsoever involved. That's this guy. And you find the limit distribution of the permuted test statistic. So you either think of just the shape of your histogram as a non-random object, or the distribution of your permuted test statistic if the data is fixed and you're drawing the G uniformly at random. So that's the same. You call these limits F1 and F2 respectively, and what we needed was to find a sufficient condition for those to match. And that was always about matching the variances of these two normal limits. So I think this summarizes it kind of well. So for the weak, so strong null when it's valid as an exact test, weak null when it's valid asymptotically, when your permutation test is valid asymptotically as the frequent test it inadvertently mimics. And the recipe is find the limit of your test statistic, call that F1, find what your histogram stabilizes to, call that F2, and give me and extract a condition for F1 to be equal to F2. That condition is a weak null. If you get an if and only if condition, then you have a kind of tight weak null, and that's what we prefer. Okay. So the first distinction I want to make is between two ways of getting at the guarantee that under the null my test statistic eventually rejects with prescribed probability. The one that we've intuitively been talking about throughout yesterday, and that we've presented formally, is really the one where we fix X and ask how does my histogram stabilize. And so the object of interest is the empirical distribution function of the permuted test statistics. So if I'm just enumerating the G's and I'm fixing the X, this is not a random object, but I'm conditioning on the realized X. And I want to ask in the supremum norm, what am I stabilizing to? Okay, so if I'm getting that, this reads really exactly as what we've been drawing on the board and interpreting. It's telling me that for my given X, my histogram is stabilizing to F2 in a way that also matches very much with what we're thinking about visually. The with probability 1 statement is over X. Why? It's very intuitive why I need that. I think you were mentioning that yesterday even. So I'm getting an X. There is a 0 probability, but still it is an event that my vector of X is 0, 0, 0, 0. That's never going to stabilize to something nice, of course. So I need an X that's not completely crazy. You can summarize that by conditions on the sample moments. And it's easy to show that the X's that will give you this occur with probability 1. And for any reasonable design. Okay. So again, there are two interpretations here. I can just think of this as a histogram that enumerates the permuted test statistic for every single permutation. That's the same thing as the distribution of TGX if I were to draw G uniformly at random, because I've just enumerated them and histogrammed them. So it's the same thing as the discrete distribution that draws uniformly at random. So I can think of these two this way. And that's really, one is the intuitive way, and two is the satisfying way, because I get this one X and I want to think about what my histogram stabilizes to. The other approach is, so let's read it from here, is not gonna guarantee this strong type of convergence. It's just gonna guarantee convergence in probability of my empirical distribution function, now thought of as random because I'm letting X be random. It's going to be a guarantee that this converges in probability to some distribution function R. And that's going to be enough, perhaps not so surprisingly, because again, the guarantee that I need at the end of the day is an unconditional guarantee. So maybe earlier, maybe I don't need to wait for the complete end of the proof to drop the conditioning on X. Maybe I can drop it in a sense earlier in the proof, and that's sort of the intuition here. And so the fact that we're going to be able to work unconditionally on X is going to allow for different proof techniques. What's the condition that delivers this? I need it to be true that if I draw an X at random from its distribution, so X is not I'm not conditioning on X anymore, I draw two permutations at random, all of these guys drawn independently. Not only is my test statistic going to converge weakly to some random variable, but it needs to be true that any pair of those, any such pair converges to two independent random variables with the same distribution. So that's the Hovding criteria. Kind of easy to interpret. It gives you a flavor that in the limit, I have something like my randomization hypothesis. Like I'm getting that all the test statistics have the same distribution and they're independent from one another. So it feels a little bit like I'm going to be able to do inference, something like a permutation test in the limit has a little bit of that flavor. So it's encouraging. In fact, going from this condition to the convergence and distribution is very just a proof of just a few lines, which we'll do in a second. Yeah. Yeah. Yeah.
Okay, sorry. Just to clarify, I think you answered this in class in the winter, but when we say that we are converging in the interpretation two is what I'm looking at, am I thinking about drawing more and more G's from this group and fixing X, or is it kind of like
which display are you looking at?
Interpretation 2.
Yeah.
Yeah, is it like I get a new N and then I get a new X and then I get a new group and I draw G's from it and I get a new histogram and that's the sense in which I'm converging and N is getting bigger?
Yeah. So this is index in N, this is index in N. I think it's more productive to just say thinking of a sequence of those things is not very attractive because there's not a natural sense of, in the measure theoretic sense there is, because you can fix a realization in the omega space, but I think the more practical way of saying that is for a really large N, I get the X, I can give you such a guarantee.
Okay.
So thinking along a sequence, I don't find it super helpful for the intuition. Yeah.
Okay.
Yeah.
Okay.
Yeah.
Thank you.
Yeah.
So one thing that I think I'm so confused about with this is it feels like the result from the PCLT implies the result from Hopkins criteria, right?
Yeah.
Because here we have uniform convergence.
Yeah.
Probability, right?
And this is even emotionally, this is a lot more satisfying.
Right.
Yeah.
And yet, it feels like the Hopkins assumptions are stronger, right? We didn't have to make this, the PCLT, am I missing some assumption? Because I feel like we have a stronger result with the PCLT, but maybe it's just for convenience of the proof strategy or something. Why would you want to use the Hopkins criteria unless it's buying you some?
Oh, well, so it's not exactly on the board here. Here I'm giving you a conclusion, and a condition for that conclusion. So I haven't told you conditions for this, really. Yeah. But at the same time, this should feel strong because in terms of guaranteeing this is necessary. So it's still pretty strong. Yeah. This? Yeah. Yeah, yeah, yeah. Yeah. No, you draw everything at random. And so the idea is that the reshuffling is such that even though you drew the same random x, you're breaking the dependence of the statistics in the limit just because of this random reshuffling.
But the statement of convergence and distribution, so what is the thing that is being taken into account when thinking about randomness? So that
Yeah.
everything distribution is xn is
Sampled from this true distribution.
and g is sampled.
Yeah, uniformly at random.
And so those distributions are like distributions of psi integrate over the xn and I integrate over the g's.
Yeah. Yeah. You're going to see them explicitly when I don't know if I'll have time to do the proof, but I'll show you explicitly. Yeah. Yeah.
Sorry, I may have missed this, but what is R of t on the right-hand side of the problem?
Yeah. Oh, sorry, it is there. It's in the same slide. It's the empirical distribution of the permuted test statistics.
But without the cat.
Oh, it's going to something.
Oh, just
Yeah. Wait, did I do this twice or what's going on? Okay. Right. So what we cited last time was a PCLT, so the proper conditional central limit theorem for the one sample test, and we saw that it was if you're doing the one sample test for the mean, where your test statistic was xi and then minus 1 gi, where gi was one of the 0, 1, one of the any possible vectors with zeros or ones in its entries. This, properly normalized, was going to go to normal, mean 0, and whatever the variance of x was. But I didn't tell you how to prove it. So it turns out it's very easy. So it's kind of just flipping in your head what's fixed and what's random. And so think of the xi as fixed, even though it was the random variable, so condition upon it. And rewrite for psychological ease of mind the minus 1 to the gi as an epsilon I. And since I'm drawing g from I'm drawing g from the set of vectors with all zeros and ones, I want to think of this epsilon as uniformly distributed on minus 1 and plus 1. And so now that's the whole trick, because now I have a sum with a known sequence. This sequence of x's, I have a strong law of large numbers for it, so I know what it stabilizes to. I have a CLT for the epsilon I, so I have a CLT for the xi epsilon I pairs, and so this must go to a normal mean 0. The epsilon i's have variance 1, and so variance of the xi's, which is exactly what I thought what we promised yesterday. So, without going into the details, the point is fix the random thing. You're able to think of this minus 1 to the g as the random thing, and then apply an off-the-shelf CLT for sum of random variables with coefficients to your object, and you're done. That's misleadingly easy, but that's a case where it works because you can think of these terms as ID. Okay, so I wanted to show you one because it gives you a flavor of how these things are done. The main point would be about PCLTs would be a different one. So if you look in your textbook, we also do the case for the two-sample test for the mean, and it's extremely challenging. So that's more the message. The PCLT approach and the Hovding approach are different. Just the fact that you have two angles of attack is helpful, but more often than not, the Hovding approach is easier. So let's consider this one now. So the Hovding approach instead says, consider the limit of t gx, where both g and x are random. The limit doesn't depend specifically on xn, but since we want unconditional validity, right, this, then intuitively, we're not so surprised that that's going to be enough. And so what we need to get is this convergence. And if you go to Chung and Romano 2013, great paper, they have some discussion of how they feel about the difference and how the PCLT is a more conditional approach, which, again, I find more satisfying because it tells you about the randomization distribution that you have, not the one that you have in probability. And yeah, but they say, after all, the permutation distribution is indeed a distribution conditional on the observed set of observation, but the Hovding condition is, and they show it in this paper, necessary for this. So they conclude it's not fanciful. So again, there's some. Bottom line is, whichever one you're able to prove is the one you should use. So as we said, that's our Hovding condition. Two permuted test statistics where all the g's and the x are random converge to two independent test statistics with the same, each having the same marginal. That's enough for convergence and probability of your empirical distribution function. I won't go through the proof in detail. I just want to mention that it's easy, right? So we were trying to get convergence of the empirical distribution function, convergence probability. Mean square convergence is enough. Expectation you get for free because you have your assumed weak convergence. You need to get that the variance goes to 0 for your mean square convergence. Again, expectation, square of the expectation you get for free. Expectation of the square, you end up with product of the indicators of this event. So product of both random test statistic being less than the indicator t, right? The indicator of the product of the indicator is the indicator of the product. The expectation of the indicator is the probability of, and so you're just taking a simple average of that. Now this is giving you the probability weight for the distribution over the g's, to your point, because they're just drawn uniformly at sample from 2 bags of g's, so m square of them. And so you're just looking at this object, which is where the thing you kind of probably in the end backward engineered as an assumption. You have weak convergence on the pairs, so you directly get that this converges to the square of the true distribution function. So the proof is not deep. The point is that the proof is very short. So in a sense, you're very close to assuming the conclusion you want. It just falls directly out of the pieces for mean square convergence. Okay, so nothing deep here. The contrast I want to make is if I go back to the one sample test for the mean, how do I get convergence via the Hovding criteria? So we've argued I can rewrite my test statistic as sum of xi plus this epsilon I that's plus or minus 1 with probability 1/2. And now I need to check the Hovding criteria. So if I draw the epsilon for the second test statistic independently, can I show that this converges to identically distributed independent test statistics? So for the marginals, it's easy. The mean of each is 0. The variance of each, so variance of the product of the variances, variance 1. I just pick up the variance of the x. And now I need the covariance, but I can show I'm going to a normal limit, so I just need to check that the covariance is 0. What's the covariance of that? Well, it's just the expectation of the product. I pick up the x squared, both epsilons. They're independent, so the expectation distributes. This guy has expectation 0, and so the covariance is 0. And so that has a more general flavor of more easily being able to find, to check the Hovding criteria. You can imagine here that if instead of, here it was very easy because I had sign flips when I was trying to proceed conditionally, but if I had permutations, the epsilon i's would not have been independent, and then I would have had to work a lot more to show that I'm close to something where I draw independent terms or use the CLT for dependent terms equivalently. So you could imagine for general situations, it's much easier to work with the Hovding criteria than with the conditional expectation. Than with the conditional CLT. But the point I want to make to you is that these two approaches exist. When you're going to face such a situation with in your problems, try both. It's not guaranteed that the Hovding is easier. Yeah. Because I have all the I don't have like a fixed sum of ones and zeros in the vector G. I have any possible combination of zeros and ones. So if I draw a G at random, I show you that the first entry is a 1, doesn't tell you anything about the other entries. So yeah, so that's not going to happen often. That's going to be that nice. Yeah. Okay. All right, so that brought us a little bit more into details about how to get these CLTs. Now I want to talk about how to make it more likely, or how to try to ensure that we have that the limiting shape of the histogram and the true limiting distribution of X, so F2 and F1 respectively, match. And let's think about that. So let's think about that at a high level, and then let's think about it through the two-sample test. So I have my Lindenberg failure distribution. Normal goes to some variance V star. My histogram stabilizes to a normal with some variance Vj. And V star and Vj may not match. So what I would want is to studentize so that both go to a normal 0, 1. But if I want that to happen, I can't change my test statistic depending which asymptotic regime I'm in. I need to talk about the two different limits of a same test statistic. So it must be that the same studentizing term, the same variance estimate, goes to the right variance in the right regime. And I'm often going to be able to get that. So let's think about it through the two-sample test. We all share this great disappointment because we took the limits, saw that the two-sample test for the mean, so the difference between the sample average in the first sample and sample average in the second sample after reshuffling, that had a nice limit distribution with some weighted variance, some variance weighting the variance of the two groups as its asymptotic distribution. And we were almost happy until we realized that the weights were actually flipped with the variance, with the true asymptotic variance, with the asymptotic variance of the true distribution of Tx. So we did not get asymptotic validity unless variances were the same or lambda was 0.5. So groups were the same size. But your kind of first guess as to a variance estimate, so the pooled variance, because the way you break the dependence by applying the permutation acts the same way on the test statistic and on the variance estimator. That variance estimator, the pooled sample, is going to go to also variances with flipped weighting, depending on whether you permute or not before taking the limit. So depending on whether or not you are, this should be a P, I'm sorry. Depending on whether or not you're in the PCLT regime or the Lindenberg failure CLT regime. So when I divide big T by V hat, this is going to cancel with this in the frequentist limit, and this is going to cancel with this in the PCLT, well, also frequentist, but in the PCLT limit. So in both cases, I'm going to get a normal 0, 1 in the limit, and that way I'm enforcing that I can put the chocks together, that the two CLTs are going to be the same and that I'm going to be asymptotically valid. Now, in terms of building methods for applied people, this is a huge game changer, because what's our new weak null? The scientific null, that the means match, and whatever moment conditions you need, which typically come from the LF-CLT anyway, so your competitive frequentist methods will also need those conditions. So what does this mean? It means we have asymptotic validity under standard conditions, but we have exact validity under weaker conditions. Only some sort of exchangeability condition, not any strict distributional form assumptions. So now we're kind of moved from the business of doing interesting, nerdy math stat to building tools, right? This is a big change. Yeah.
What I find really cool about this is that we saw this disappointment, as you pointed out, that we needed our variance to be equal, or we needed the lambda to be equal to 1.
Yeah.
So we changed our test statistics so
Yeah.
that we get one of those two conditions.
Yes, we got the variance to equal. Yeah, that's right.
I'm wondering, just out of intellectual curiosity, how would we change our test statistic to ensure that lambda would be equal to 1 half? Would one possibility be, I have these two different samples of size n and m.
Yeah.
Let me choose a number, p,
Yeah.
that's less than n and m.
Yeah.
And randomly choose p out of n from one group, randomly choose p
Yeah.
out of n from the other group,
Yeah.
and only construct a test statistic with those p observations. Would something like that?
That would be interesting. There certainly might be ways of doing that. Then it's going to be very complicated. How do you recombine that? Well, first of all, you can throw the data in the garbage and have the sample size be equal. Okay, you don't want to do that. If you pick the subgroup at random, can you somehow average after, this has a raw realization feeling? Maybe it's possible. That seems like more complicated than this. What seems definitely would be simple but too good to be true would be some sort of reweighting where observations in the big group count for like m over n plus m of an observation. That's like emotionally tempting, but that does sound too good to be true. But that's a good question to ask. So we enforced one of the two sufficient condition. What would you need to enforce the other? Yeah, that's a new question, so that's great. Yeah. Okay. So we gave these two examples. I just want to kind of point to another one. What if I wanted to do this for things that, as applied economists, we are more ubiquitous in our world? So what if I wanted to do these things for regression? And that's going to be very much at the center of my talk at the conference part. So if I want to do this for univariate regression, then I let those be vectors. So this guy would be in Rn. And X also is in Rn. How would I build a test statistic for this? Well, I kind of have this idea that if I take out x1 beta 1 from y, then all I have is my error. If I took out exactly the right amount, let's call it beta naught. If I took out exactly the right amount of x1, there's no x1 left. I just have the epsilon left. And if I ask how does this covary with x1, then I'm going to have something that has like would have a predictable distribution under the null. Why would I have power under the alternative? Well, if I took out the wrong amount of beta 1, this is not just epsilon. This is x1 true beta 1 minus beta 1 naught plus x1, plus epsilon. And so this is going to get very big if the beta 1 naught is very far from the true beta 1. Under the null, I want to build a randomization distribution. So what am I going to do? Well, I'm going to say x1 under the null, I want to think of it as independent of the errors. So it's also independent of permutation of the errors. some kind of backward engineering a strong null here. My strong null for this to be test statistics that are going to build a histogram of identically distributed test statistics has to be that x1 epsilon. If I, again, these are vectors. If I keep the x1 fixed, I can permute the epsilon, and this has the same distribution. So if I run the randomization procedure with this test statistic under this strong null, I'm back in the framework from before, and I get an exact test for the univariate regression. Okay, that's nice, right? With the tools we built, we could do that in 2 seconds. I can take a limit of this thing. What am I thinking is going to break? If this breaks in the limit, it's because of what? It's because x, my covariate, is not independent of my epsilon along for any given entry. So I'm still thinking of ID data. What's that? What's the econometric situation in which I don't have independence of x and epsilon? I'm not thinking of endogeneity. I'm still running a bona fide regression. Yes, thank you. Heteroscedasticity. If I have heteroscedasticity, I'm not going to get asymptotic validity directly for this guy. The variances are not going to match. I need to studentize. Why? It's kind of obvious, because I won't have heteroscedasticity for the permuted test statistics, since I'm not lining up the x's with the epsilons anymore, so they're not dependent. But if I studentize by the heteroscedasticity robust variance, when I don't permute, so in the identity regime, I get the usual limit for the white heteroscedasticity robust estimator. But if I permute, I'm acting as if on independent data, so I also have the right limit to correct for the variance of my test statistic. And so I've applied my strong null intuition, my weak null recipe, and I've been able to build a studentized test statistic so that I have the full apparatus for a permutation test for the univariate regression. So very nice, right? We can use our tools and our intuition right away. And this works. Okay. Great. So what do we want? Principally, we want the asymptotic behavior of proposed studied randomized test statistics. There are 2 ways to produce the limit distribution. The consensus seems to be that in most, but not in all cases, Hovding is a little bit easier. And for permutation tests, you're going to have to need coupling arguments to get and coupling arguments. Sorry, for permutation tests, coupling arguments generally guarantees that it suffices to show Hovding criteria for IID data from the marginal. That's sort of the message of Chung and Romano. Yeah, and then the weak null was a sufficient condition for the LFCLT and the PCLT, or the Hovding limit to match. That's a recipe for finding a weak null. We were able to weaken the weak null by studentizing, and we saw 2 cases where we brought the weak null back to the scientific null, which means that now we're building methodology that's competitive with existing practice, but is valid more widely. So that you need to be the case that not too much power has been forgone to get this wider validity. Okay, any questions about this before we?
So we saw 3 different examples. The 1 sample mean, the 2 sample test for equality means, and then the univariate regression. And in these 3 examples, whenever we could do a randomization test, we also had the usual frequentist version of it, and that allows us to, appeal to this asymptotic validity and compare the book.
Yeah.
I'm wondering if there are examples where we don't know how to come up with the asymptotic distribution. Are there settings in which, like, we can't do the frequentist stuff, but we might get exact validity with the randomization inference?
So that's the thing we were talking about yesterday. So there are cases where you, in practice, don't want to compute what's plugins for your frequentist limit. So purely procedurally, it's going to be easier to effectively simulate, to run a permutation test instead of computing an asymptotic variance. But to show that this works, you still need to show in theory that the limits match. Okay. Yeah. So yeah, that's the best answer I have to that question. Okay. Anything else? Okay, perfect. We're almost right at midtime. So, okay, so this was technical, but I think it's really the technical insights you want to have, at least at a high level, for when you go back to this material and try to disentangle it, because you'll see papers that sort of use the Hovding approach without mentioning that they could have used the conditional approach and vice versa. So if you want a kind of mature take on this literature, it's good to know. It's good to have had the conversation we just had. Okay, so now we're going to something much more conceptual. So kind of changing topics, changing gears completely here. If you think of the two-sample test, we really ran it as two groups, reshuffle people between groups, take the sample average again, do that as many times as you can to enumerate the assignments, build a kind of placebo-like distribution for that, and get quantiles from that. Mechanically, this is the same as running a Fisher test. So what's different? And if we move to Fisher and randomization tests for things other than the difference in mean, are there going to be methodological differences? Why are these things so similar yet different? Can we sort of give a unified treatment to understand conceptually what's the difference? And with the application to OLS, we won't have time to do IV today. But it's going to be essentially IV, since you need to think of random assignments for the Fisher test interpretation. Okay, so Fisher test, we thought of our randomization inference as acting upon observational data. Fisher test, it follows an experiment. Treatment must have been randomly assigned. In a sense, that's the only source of randomness, because we're going to think of the people's outcome, counterfactual outcomes, as fixed or at least conditioned upon. So if the treatment effect is 0, and I have two groups, then treatment assignments is just randomly assigning labels. And so that's thinking of a 0 treatment effect without loss of generality. And so by randomly assigning these labels, reassigning these labels, and recomputing the test statistic, we can produce what? All the test statistic realizations that might have had a cure with equal probability under the null hypothesis. This histogram is not a randomization distribution anymore. It's a bona fide null distribution. This is all the values of the test statistic that could have occurred under the null with this source of variation. Yeah.
So this is the null that every treatment for every person is sick.
Yeah, that's a sharp null, yeah. Yeah, I'm not gonna, yeah, it's what you're going. I'm not gonna talk about trying to do Fisher type stuff with a null on the average treatment effect. I'm just trying to compare the true Fisher test with what we've been talking about for the last 2 days. Okay, so this Fisher test, for the of you who show up, each subject has potential outcome y0 and y1, and the procedure and its validity are going to be conditional on everybody's potential outcome. So conditional on the data, even though only half of this data is observed, and then under the sharp null of the 0 treatment effect, I know yi0 if I see yi1, and vice versa. So if I'm doing A/B testing, two-sample test statistic, what I observe is the yi1 for the people who were randomly assigned treatment, the sample average of those guys, and then the other people were assigned no treatment. I take the sample average of those guys, and I take the difference, and that's my test statistic. And if I'm looking for any effect, not just positive effect, I can take the absolute value. There was a support for the treatment assignment. Maybe it was completely randomly assigned. Maybe I was blocking on gender. Many possibilities. I can enumerate those with multiplicity if needed, and I draw my treatment assignment uniformly from that support. What's the p-value? How do I get a p-value? Well, I ask, of all the test statistics that could have occurred under the null, what's the probability of seeing something bigger or equal than what I've seen? And since I've completed the data with the sharp null, and I'm drawing the treatment assignment from the true treatment assignment mechanism, this is a bona fide p-value. And the histogram of these guys is a bona fide null distribution. So the test is just the indicator that I'm above the 1 minus alpha quantile of this distribution. Right, so collected the same way I did before. It's very reminiscent of the construction. It's identical to the construction. The construction is the same. Yeah. If calligraphic Z is all possible assignment of 20 treatments to the 40 people, it's mechanically exactly the same. Yeah. And then what am I getting? Well, remember, it's not an invariance argument where resampling permuted and unpermuted X's are the same. Randomness is coming from treatment assignment. So if I keep the Y's fixed and I take the expectation over all possible treatment assignment, then I'm just asking how often my test statistic is bigger than the 1 minus alpha quantile of its own distribution. Mechanically, that's alpha, with no group requirement involved in any way. So, no group requirement, and the validity being conditional on the people who show up at the experiment, you should think of as a stronger conclusion than the unconditional validity, simply because conditional validity for any condition implies unconditional validity. And it may be that you are actually interested in the effect for the 20 people who show up to your experiment, not just the effect on the superpopulation they're drawn from. So you might be interested in conditional validity. This stronger assumption, this is because you need experimental design, strictly stronger assumption, as we discussed actually, buys you that. Yeah.
I think you kind of answered my question. What I was going to say is, so we run a numerically equivalent procedure, and we basically have two ways to interpret it.
Yeah.
Right? And I can see,
Yeah.
psychologically, I can see either way being beneficial, because like you said, the conditional validity implies unconditional validity.
Yeah.
But at the same time, usually you're not interested in the treatment effect on people who show up to study. Like
Yeah.
That's, when you publish your paper, you're not saying, I'm studying the effect of this 20 people.
Yeah, on Robert, Frank, Jane, and Julie. Yeah, and I agree.
So I'm just wondering anything about trading off the
Right.
I feel with any design is everyone's
Yeah.
I think it's like usually kind of dubious, like what the interpretation is, or like.
Yeah, so a motivation in that literature might be that there is no superpopulation, like the states in the US, and there's no like bigger bag of states. For the more natural applications of this thing, I think I agree with you that I'm probably interested in the superpopulation parameter. Pedagogically, I chose the narrative that like there may be people who are interested in this stronger condition, like these people come in, I try the drug on these people, I saw an effect. What's the chance that what happened in this room was a fluke? So I agree with you, but I want us to agree that these people exist and who want conditional validity, and they need this tool, the Fisher test. Are they our friends? Do we know them? I know. Yeah, that's another question. Okay. What's going on here? All right. So let's go back. So now we've refreshed or learned what the Fisher test was. Let's go back to the randomization test. For randomization test, there's no notion of fixing variables and potential outcomes and then randomly assigning treatment. We get observational data. So we sample the data and test a feature about its DGP, and what we're getting information about is the superpopulation. So the question of interest is unconditional in nature. It's about the population from which our subjects were drawn, and so the validity is also unconditional. Invariance to some transformations, our group, the group elements, obtains under the null, hopefully only under the null, and the set of all transformed and therefore independent statistics from the randomization distribution. I think I'm using this term a bit loosely here. Okay, so it's not necessarily a null distribution, and that's already a first contrast with the Fisher test. So unless you have a rank test, there's no reason to think that you have a null, that your randomization distribution is a null distribution. And again, as was just observed, procedurally it's going to look very much like the Fisher test for A/B testing, just in different notation. So we get our data, the X and W's, concatenate that in a Y. We want to test that the mean in both groups is the same. As we saw yesterday and this morning again, the strong null that we need for this, since we need the reshuffled vector and the not reshuffled vector to have the same distribution, well, it must be that every entry has the same distribution. And so we're asking that both groups not only have the same mean, but the same entire distribution. And our test statistic is, again, the same as in the Fisher case, just the difference in sample averages. Yeah.
Each person.
Yeah.
And so if there's a superpopulation, the superpopulation is typically IID draws over the vector of potential outcomes and treatment assignment.
Yeah. Yeah, that's right. As treatment assignment being drawn independently from hopefully the Y's, but yeah, exact, yeah. Yeah. So to get the two things to fit, I need to think that people show up, they have their pairs. I draw the treatment random assignment to decide which counterfactual I get to see for everyone. And once I know that, I stack the 0 guys here and the 1 guys here. Yeah. 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 No, you show up with your two counterfactual outcomes, and then I flip a coin in front of you, and you show me the one of the two outcomes that corresponds to the head or tail.
But then the indexes are going to change, no? Like, what is going to be the X and the W populations? Don't I have to define the set of all I's such that D9 equals 1?
I don't think there's a problem in building this vector and relabeling after having seen the treatment assignment labels. That's what you're concerned about? Okay. Under the null, a definition matter if I'm permuting after, but I should think about whether that's specific to actually not caring about indices because of the G I picked. Okay, so that's fair. But clearly here is not going to be an issue. Okay, and then the randomization test we saw, and again, I'm kind of, very intentionally using overlapping notation. So I get my test statistic where the permutation is the identity. I look at all permuted test statistic, pick the 1 minus alpha quantile of all the permuted test statistics. If I have my strong null, so randomization hypothesis is satisfied, and G is a group, we've shown formally that this is going to give me unconditional validity, so over an expectation over Y, the test is going to reject under the null alpha of the time. So so as we were discussing yesterday, the procedure is conditional, unlike for a t-test, classical t-test, but the validity is unconditional. And that's unlike for the Fisher test. The Fisher test, the validity is very much conditional on the Y's, the pairs of potential outcomes. Yeah.
I think it might just be asking each other's question, but if you go back to the previous slide, when you were writing down what it means to be unconditionally valid, you're taking that expectation just with respect to the outcome data. But if I'm taking a look at the data that I have on my computer, the CSV file, I'll have the outcome data as well as which treatment group you're assigned to. And so if I wanted, so this is unconditional on the outcome data, but do we still condition on the actual treatment assignment?
Yeah, give me 2 seconds and I'll make it formal. But the answer is no, because whether I reshuffle the entries and keep first group, second group separate, or reshuffle the entries and reshuffle where the groups are. It won't matter. Yeah. Okay, so we want a unified treatment. So we want to provide a unified treatment of Fisherian and randomization inference. We've already started like hinting at that by using overlapping notation, but now I really want to start making connections. So both procedures in the two sample test, and I agree that I might be leveraging more than two like specificities of this example. So I'll do my homeworks and be careful to see what are the full generalizations of this. But both procedures are almost identical, but the assumptions differ and the guarantees differ. So are the assumptions of one method strictly stronger? We've already answered that, yes, for the Fisher test. And if so, can the method interpretations, the weaker assumption, be used as a sort of robust alternative? The answer is going to be yes there too, and that's going to be our first kind of productive connection with methodological implication. Okay, so validity of the Fisher test, take the expectation over Z, now take the expectation over Y2. Iterated expectation, fx y for any y, run my Fisher test. Mechanically, that has expectation alpha, can take the expectation over y, so I have unconditional validity. But we knew unconditional validity implies conditional validity. A bit more satisfying, as we had discussed in class. It's not just that the implications imply one another. The sharp null, in fact, implies the randomization hypothesis. So that's actually even more satisfying. Okay, can we get in trouble? Well, what does it mean for a Fisher test to be misspecified? And can we think about robustness for misspecified Fisher test? So suppose I have the full menu of counterfactual. Yeah. Yeah. So it could, without loss of generality, it could be. I could have heterogeneous treatment effect as long as I know all the individual treatment effects. Yeah. Okay, so I have Robert, Ryan, Julie, Jen showing up to the experiment. This is their menu of counterfactual outcomes. And I have two treatments. And so the treatment assignment vector could be 1, 0, 1, 0, 0, 1, 1, 0, and so on. That's what I think I know. And then I can run the permutation test. I'm not saying whether it's Fisher or randomization. And I can compute the value of the tested state, right? 1, 0, 1, 0, that's 4 minus 2 plus 10 minus 2 divided by 4, by 2. And so that's if all treatment assignments were equally likely, this would be my null distribution. And I can run this thinking that assigning two vectors, two treatments to any of the 4 people is the experimental guideline. This would be my null distribution. I compute the p-value, and it's 5/6. But actually, the experiment was poorly documented, and I had to balance between guys and girls, and the treatment assignment was only randomized over A through D, and the true value is the true p-value under this null distribution is 1, not 5/6. So I'm wrong. I misspecified the treatment assignment mechanism, got the wrong p-value, suggested the wrong policy, and the country elected Trump. So very bad consequences. So I need to do something else. I need to ask, is there a way in which I can be robust? Well, here I was, because going back to the observation that's been made, what I ran, even though it was not a valid Fisher test, was still a valid randomization test. And I didn't get conditional validity, but I did get unconditional validity. So as long as your treatment assignment mechanism corresponds to random assignment over a group, even if you're misspecified in your treatment assignment mechanism and therefore have to forego conditional validity, you can still have as a backup unconditional validity. And so this is kind of building even more of a connection between our two worlds, because remember, we had the strong null for randomization test, and that gave us exact validity, and now we're very careful to say that it's exact unconditional on Y validity. And we said, well, if my strong null doesn't hold, I have as a robust alternative my weak null, the possibility to satisfy my weak null, and that would give me at least asymptotic validity. Now I've completed this because actually this strong null is a robust alternative to my Fisher, or let's say sharp null, which guarantees me something even stronger, exact conditional validity. So really starting to put these two worlds together and connect them in ways that have practical implications. So we can push this a little bit more, going through this thought example and thinking like of having to pick a design. So here we kind of whirl a key, but it may have implications in the choice of design. So suppose there's uncertainty. So something I did for the relevance that's relevant for practice. Yes. If there's uncertainty as to the treatment assignment mechanism, you should of course favor one that corresponds to sampling uniformly from an algebraic group. So this means that you have your realized treatment assignment vector, and you want to be able to build a support by drawing transformations of this realized treatment assignment over your group actions. So suppose you're working at Facebook, very modular enterprise, people work fast and break things, and you go fetch results from an A/B test, and it's poorly documented because they work fast and break things, and there's 1,000 units, and 450 of them are treated. And the documentation says everybody is treated randomly. And so is it that there was a budget of 450 treatments randomly assigned, or people came in the room and I flipped a fair coin or a weighted coin to decide if they were treated or not? But how do you run your test? Well, now we have an answer. In doubt, the recommendation is to run the Fisher test using the fixed allotment of treatment. So if that's one of the, in your mind, equally likely treatment assignment mechanism. That way, if you're misspecified as a Fisher test, you're still running a valid randomization test. You get unconditional validity as a robust interpretation, foregoing the conditional validity of the Fisher test if you were misspecified. And to our discussion before, maybe that's all you cared about in the first place. So maybe maybe you get this robustness at no cost. So that's a practical implication for picking G in the admittedly specific case where there's uncertainty about the treatment assignment mechanism. Let's go to a case that maybe is much more common. So if you looking for people who are working very intuitively with inference and regression, you can look at the political science applied literature, and there you have test statistics that are going, you're going to have people trying to run placebo tests, Fisher tests, and there's a real desire to make these things formal. And so one place where you find such examples, so Chris Berry and Anthony Fowler have a paper in some sort of Nature topic journal. It's a very nice paper. And they're interested in running permutation tests for OLS. And so they have examples like, I want to know if this QB, if QBs matter for winning games. And so they have data over time, and they have indicator dummy for which QB was playing. And so there you have something like, Y is winning the game, and you have your QB indicator, and you have your value for that effect under the null, and you think that the QB is as if randomly assigned, and they really want to run this as a conditional procedure for conditional validity. So that's their test statistic is a little bit different, but they're essentially running this. Okay. So whether I want a Fisher test, because I think the QB is randomly assigned, which, whatever, or I want the nested, slightly weaker setup where I think that x1, the vector, and the error has the same distribution as x1 and permitted error, which I get under the Fisher null, right? Then, okay, so if I have that, if really the QBs are randomly assigned, as if experimentally or just somehow this holds, then the histogram of these guys is going to be a bona fide Fisher or randomization distribution. I can pick up quantiles that are going to be bona fide p-values. Okay, let's think about whether I believe this. What do I need for this to be true? Or put otherwise, suppose that the coach matters for winning, and the coach, who the coach is correlated with who the QB is. If there's OVB, first of all, I'm not going to estimate the point estimate I want. There's a much more fatal flaw. This is not going to hold, right? If I'm missing an x2 that's correlated with x1, and I'm thinking of running this model, then my error is effectively this. x2 is correlated with x1, and I have some x2 in the epsilon, and there's no way this is true. So out of modeling interest, I might want an x2, but out of the mere validity of the procedure, if there's an x2 that's bringing omitted variable bias when it's not there, I need to bring it in. Okay, so I need to bring this guy in. So clearly, my randomization hypothesis is going to be something like this. That's fine. I know how to extend this. What's my test statistic under the null? What's here? It's not the curveball. So I have the epsilon. That's fine. That I'm happy with. My epsilon is independent of my x1. But I'm in the bivariate model here. So what's in there too? Yeah. When G is the identity, this is correlated with this. The x1 and x2 are independent. When I permute, I break this independence. And so these test statistics are not even distributed the same under the null. This test statistic does not work for testing this null under the natural strong null. So now I don't just change my mind or pick the right group. I need to sit down and I need new methodology. I need a new test statistic. And the key is going to be find a way to be entirely invariant with respect to beta 2. Doing that takes 45 minutes, so we'll do that at the conference. But that's the cliffhanger I kind of wanted to leave you on. So easy to consider Fisher and randomization test. Yeah, sorry. Yeah. If I had to test the whole vector, I could literally just think of this as a matrix instead of a vector. Yeah, correct. That's a good point. That also means I could do projection and get individual contrast interval, but projection is extremely conservative. And I think what's reduced form regression for covariates is not outrageous at all. Projection with 4 dimension is extremely conservative. Okay, so easy to consider. Fisher and randomization-based inference is the same framework. You just need to think that the 20 people who showed up to your experiment are not the only 20 people. There's a whole world out there of people that they were drawn from. Immediate implications arise. So exact randomization inference under the strong null obtains as a robust backup to Fisher tests. The same way the asymptotic validity under weak null was a backup to exact validity, to exact validity under the strong null. So it's very nice. We're really bringing these two worlds together. In easy cases, same methodology, new interpretation, right? That was the case of the Fisher test where I have a fixed budget of treatments that's completely randomly assigned. If your treatment assignment is a bit more complicated, just make sure that it corresponds to an algebraic group. But in the next hardest case, I want to do LS, then we need completely new methodology, and the problem is non-trivial. So there's kind of a whole line of work if you believe you want, either you believe you want this robustness, or you want to be serious about doing permutation type tests on observational data. There are a lot of standard cases where you need to sit down and develop new methodology. And these, I think, are very beautiful questions, and we'll see one of those at the conference. Okay. 10 minutes before, so perfect. That's what. Sorry, I went a bit fast, but happy to take questions. Yeah.
Could you go back to the Amazon example that you had? I think it was the Amazon example.
Facebook. Yeah.
Very
Very different. No, yeah.
The recommendation was to run a Fisher test, and as a robustness interpretation, we would have unconditional validity.
I think my client wants to run a Fisher test, and I'm saying, if ex ante you're indifferent between the treatment assignment, which was your suggestion actually of like flipping a coin for everybody versus allocating uniformly at random a fixed number of treatment, the same number you observed, then do the latter because you're robust.
Sorry, what was the latter?
I have 1,000 people, 450 treatment assignment. I just reassigned the fixed lot of 450 treatments at random.
Okay.
That's like permuting the vector of treatment assignment.
Okay. If I'm running the Fisher test, I would need to take a stance on what it is my treatment assignment mechanism is.
Exact.
And wouldn't I then know if that, I think you call it calligraphic Z, if that is equal to the set of group actions that I would need to consider when running the randomization test?
Yeah, that's the point. So you don't know what was the true treatment assignment mechanism. It might be one of many things. The one you're going to use, can you write it as calligraphic Z is all, let's say, permutations or some other group actions applied to the observed treatment assignment vector? If that's the case, this one's going to be robust even if misspecified.
So it seems like if I'm following correctly, then it seems like the recommendation would be to do the randomization test.
To what?
The recommendation would be to do the randomization
Yeah.
test. And if it's the case that your treatment assignment mechanism was truly
Yeah.
the script key,
Yeah.
the set of all groups, then we get the conditional validity that
You were saying the same thing.
we are. Okay.
Yeah.
Okay.
Either you have the more general thing if you're wrong, or you start with the general thing and you have the more specific thing if you're right.
Okay. And that kind of like two-way street is very akin to the sharp weak.
Yeah, exactly. Yeah. We're having a similar discussion. Exactly. Yeah, that's right. Yeah.
Could you go back to the example with the, you had the specific numbers of p happening by 6 and, right. I don't think I followed how you were computing the null distribution and where those numbers were coming from. Here, in the toy example where we see y1 and y0 for each individual, we know that the sharp null is incorrect because y1 and y0 are different for each individual.
Oh no! This is I filled this table with the sharp null.
You fill this table with the sharp null.
This is the
I see.
There's no. I'm not wrong about the. I'm not. Yeah.
Got it.
This is the true counterfactuals, and I have the correct null.
Okay.
Yeah. Okay, that's actually a good presentation point because they would be, yeah. Okay, but I can make that slide clearer. And then want all twos on the. Okay. Any other questions?
I have
Yeah.
maybe a bit of a question.
Yeah, yeah. So, so yes and no. So when we were doing the median test, so there's two-part answer. When the two examples we saw where we're doing sort of one sample test for the median, one sample test for the mean, and in order to be valid, we match the asymptotic distribution of the unpermitted test statistic. Since the test statistic we started with is the standard one, then there's no loss in power. If we move to this world and we need to modify the test statistic to by invariance, we're going to have to do things to it that will cost power. So that's the answer, yeah. So invariance to parameters you want to other coefficients that you want to not show, that you want to be pivotal with respect to, in this framework, it does not come for free. Yeah, that's a great question. Okay, any other question? All right, happy to talk more about this. Obviously, I love this stuff, so we can talk offline. Thank you very much, guys.